Okay, lecture 5. Uh, Sometimes I feel that we are very lucky to have the planar MOSFET because this system, the Poisson equation itself, is a nonlinear differential equation. So its analytic solution is, in general, not available to us. However, fortunately for planar MOSFET, we can have a very good and concise expression for charge density. That is one of the big reasons why we have quite good models for as this MOS system. So of course, I wanted to say that today we will see the exact result, but it is not available to everywhere. So before starting today's lecture, I wanted to just tell you the limitation of our approach. For example, although we say that this is exact and very beautiful, but there are some missing factors. One was in this structure, we have assumed a uniform doping density of Na. So accepted density is just constant all over our structure. So in this case, this is go to infinity, and this one is equal to x equal to 0. In this case, we have assumed a uniform distribution of dopant density, but in reality, this Na itself can be a position dependent quantity. Intentionally, we introduce a position dependency of accepted density inside this system, but we neglected that information. This is one limitation. And another limitation is we have assumed that this is positively infinite. So it means that we have thick enough substrate for our MOS system. But previously, when we talk about planar MOSFET, that was fully justified. But nowadays, this is not the case. So the real thickness of this silicon layer nowadays, everybody should know that this is about just 5 nanometer thick. So compared with several hundred nanometer, currently we are assuming this is extremely short, and this is terminated by another oxide layer. Here we have oxide, and here we have oxide, and terminated by one gated material and another gate material. Of course, they are the same material, but anyway, geometrically we have two ends terminated by metal and metal. So if we think about the applicability of our planar MOSFET approximation, so this is not the general one. So we have to generalize this kind of consideration for more general cases, but I wanted to say this one. As much as planar technology is involved, then we can live with this expression with minimum modification. Of course, if we have just uniform accepted density, then it's good, just perfect. But for example, we can introduce intentionally certain amount of additional accepted density just nearby the surface region. So we can introduce this kind of thing, or sometimes even we can introduce some reduction of doping density nearby interface. This kind of spatial variation can be introduced to adjust the threshold voltage of our technology. Then what can we do is just to modify small, a little bit our today's result. So that is one thing I wanted to say. And as much as planar MOSFET is concerned, then this today's expression is quite much acceptable even with doping density modification. And if we go to the real different structure, like terminated by certain other oxide layer and terminated by another metal. In this case, we have to develop fully different approaches, different formulation for this system. So that is a topic of another session. So I will not talk about it today's lecture. But important point is having this kind of a fully analytic result is quite good for us to make a reasonably simple and accurate expression for our MOS system. So this is very important, and all of our discussion throughout this semester will be based on today's lecture contents. So everything is just a simplification of today's expression into more acceptable way, and by using that approximated and simplified form, we will try to develop more advanced topics like drain current and other kinds of short channel effect. Okay, so today's lecture content is quite important in this sense. But today's lecture already covered partially in the previous lecture L04. So I remember that we have already covered this geometry. So we assume that x equals 0 as the interface between silicon dioxide and silicon, and assume that our silicon layer expanded up to positive infinity. And if we go to positive infinity, there you can find a uniform substrate. So since this is uniform and much higher than intrinsic carrier density, what you can expect is, okay, so hole density would be quite similar to that of uniform doping density. So and also electron density. So since this system is at equilibrium, so that should be so Ni squared divided by hole density, of course, and this is corresponding to Ni squared and A. You know it. So more or less electron density and hole density at the endpoints are given, and of course, since hole density and electron densities are known, it means that in this case, in this equilibrium case, we already know the value of this electrostatic potential. If I ask you this, how can we measure or calculate this electrostatic potential? What should be your answer? Your answer should be, yes, this is the hole density at that infinity point, and according to our general expression for electron density or hole density, it should follow this form. So please have a look at this negative sign, because this is corresponding to our hole density. If we are talking about electron density, then we have to consider positive sign, but since this is electron hole density, so simply speaking, this equation states that hole density is equal to Na, and in order to have this Na density of hole, our electrostatic potential should be adjusted. So that is quite easy and simple. So starting from this expression, what you can do is just do simple manipulation. Ni exponential something. Yes, I am certain that you are much better than me in this aspect. And taking the log, so in the both side, so you will have just Na over Ni, and that will give us minus phi divided by kBt over Q. So now you can find that your potential at infinity point is just given as given number, that is minus times kBt over Q and log over something. something means that, so just to normalized acceptor density. Simply speaking, if you have even higher acceptor density, then this log term will increase, and since you have a minus sign in front of it, so you will have the negative value for your more negative value for your potential. So if you have a 10 to the 17, then you will have a certain value, and if you have a 10 to the 18, then absolute value is increased and go to the negative value. So that is the boundary condition for this endpoint, and we just to say that this is equal to, yes, this value is denoted as minus 5b in Professor Tower's book, and this is quite much commonly used notation for this one. This b, why that is called as b, maybe that is related with banding, so band banding, but I have a little idea about its historical reason. But anyway, that quantity is usually written as 5b, but the name itself is not that important. This 5b simply means that at that point, so potential is given as a certain number, and it's a negative sign. Okay, so any question up to now? So this is nothing related with the MOS system. We are now just talking about far away from a position far away from interface. So this is just argument related with the local equilibrium. Hole density should be equal to the acceptor density, and starting from that simple argument, we can calculate this 5b value. That was our setting for boundary condition. And now let's go to our Poisson equation. If we visit Poisson equation once again, and in between, you know that I silently introduce a new new reference for electrostatic potential. So although that is still written as phi, but now this phi, I will say that phi tilde should be interpreted as the general one reference to that of infinity, the deep substrate value. So if I am allowed to write it down once again, then I would say that since this is negative phi at infinity is given as a positive phi b, so I will say something like this. Okay, so now you have a Poisson equation here. We stopped here, and the main point was originally the Poisson equation should be considered as an equation with 3 unknown variables. We have no idea about electrostatic potential. We have no idea about hole density, and we have no idea about electron density. These 3 variables are our unknown variables, but unfortunately, we have only one equation. Same happens again. Poisson equation needs 3 different, in order to get information about our system, we need 3 equations: electrostatic potential, hole density, electron density, but we have only one. We need 2 more, and these 2 more equations are obtained from the expression for electron density and hole density valid at equilibrium case. Only at equilibrium case we can find a good relationship between electrostatic potential and electron density, or electrostatic potential and hole density. So by combining them all and just to insert these 2 relations into the original Poisson equation, now we have clearly one equation. This is the same one, same Poisson equation, but written with respect to just phi. actually our new phi tilde value, reference to the deep substrate. This is our case. Then if I ask you, what is the value of our potential at x equal to 0? So we have no idea. Oh, we wanted to know it. So just to call it as surface potential. We will try to measure the electrostatic potential, surface potential referenced to the deep substrate. That will be our major concern. So we will try to calculate this phi s value eventually. And then another question is, what is the value of this tilde phi at infinity? So in this case, boundary condition is quite simple, because in this new notation, reference is deep substrate. So therefore, at that point, that is referenced. So just 0 is obtained. Sorry about this kind of a new variable called, as I'm writing down, tilde phi, and this is actually not appearing in our textbook, but distinguishing their differences is quite important, because many engineers, actually students and engineers, are failing to make a clear distinction between certain value referencing and certain reference value. But when you just mess them up, then what will happen? Usually when you mess them up, you will have the errors of your delta phi kbt over q. So are you with me? For example, if you add 0.5 volt difference in your two different notations, then what will happen? Your electron density will show the difference of orders of this one. Then it is corresponding to, roughly speaking, 8 orders of difference or 9 orders of difference occurs due to your wrong interpretation about a certain value, electrostatic potential. So understanding its reference value is quite important. So please try to make a clear distinction. Okay, so I think that was the lecture progress of our previous lecture. Then now we have to solve this Poisson equation. But solving this Poisson equation in general would be quite difficult, because this equation itself is quite non-linear. Where can you find the non-linearity? Because here we have exponential dependence of electron density, hole density on electrostatic potential. This is nothing but originated from hole density. And this one is originated from electron density. Since they are exponentially depending on the electrostatic potential, in general it would be very difficult. So I'm just showing you how can you quickly solve this problem. So in my opinion, from this slide 3, we are really entering into today's lecture main contents. But before doing this job, so I will show you more simpler one. Here we have a Poisson equation, and in this slide number 3, so we will try to make certain integration later. So what we will do is integration. Integration over what? Integration over real space, starting from x equal to 0 and ending at x equal to infinity. We will just make an integration over something. That's it. But please have a look at this slide. In this slide, we will, before taking the integration, we will do certain thing. That is the point. So before talking about this equation 3, the equation shown in slide 3, I will just do another one. So let me just come back to our original Poisson equation. Here you can see that this is corresponding to, maybe you can find rho and divided epsilon silicon. This is the form of a Poisson equation in its original form, and the form shown equation 4.9 is just obtained by including some expressions for this law, net charge density. Net charge density is obtained by hole contribution, electron contribution, and doping contribution. These are shown here. But before considering this one, let me just write down here square, and silicon and rho x. This is Poisson equation. As I advertised already, today we will try to integrate this equation over certain length scale. So let me just do it without performing anything. So I'm saying that why don't you just introduce this operation, integrating this equation over real space starting from 0 to whatever, okay, for example from 2 0. Then let me just do it. This left hand side becomes, it was a second derivative and now it becomes just first order derivative. So we will have the first order derivative evaluated at x equal to infinity minus, so first order derivative evaluated at x equal to 0. That will be the left hand side term. You know, this guy will give us these two terms, upper limit and lower limit. So it is quite much easy to understand. And let's go to the right hand side term. Here we have 1 over epsilon silicon and just integration of our net charge density all over our position, all over our substrate. So are you with me? So we have a simple second order differentiation, and by integrating once we will have just first order derivatives, and their differences at upper bound and lower bound will be the left hand side. And since there is net charge density, then we will have just integration of the net charge density. And I'm asking you, please try to understand what are they. Here we have derivative of electrostatic potential at infinity. What is it? This is nothing but just negative electric field. You should know that electric field is given as this form, and if we just project that into our x directional point, then Ex should be minus d phi over dx. This is nothing but just the electric field and its negative value. And I'm asking you, what is the electric field at deep substrate? If you go deep into your planar MOSFET substrate, how much electric field can be expected? The answer is obvious. Because this is deep substrate, there is no variation of physical quantities, and that should vanish. So simply speaking, this one is not allowed to existing. Yes, so we will have just this simple form. So simply speaking, now we can say that this relation, the integrated Poisson equation gives that gives us this simple relation. Electric field, x directional electric field evaluated at x equal to 0. This is the one, is given as minus 1 over epsilon silicon and integrated charge all over our silicon region, substrate region. And fortunately, we know this quantity. What we know is this, for this quantity, we have already introduced a certain quantity. What is it? What is integrated net charge density over our substrate? That was denoted as, this one. So total charge inside the semiconductor region. So simply speaking, when you integrate your Poisson equation without doing anything, just to integrate it over your silicon substrate, then you found that surface electric field, the electric field measured at the surface, is equal to nothing but your total charge normalized by your silicon permittivity. So there is a one-to-one correspondence between surface electric field and the total amount of charge inside this silicon system. That is key observation by obtaining, integrating our Poisson equation only once without any weighting factor. Okay, are you with me? So this is you have seen this kind of argument so many times. I did it with one-dimensional system explicitly, but maybe you have seen it before like this. So please allow me just to do it in a three-dimensional way. So if you integrate, make the volume integration of this quantity, this is volume, and this one becomes just volume integration, and you will have just QS. And what is this? This one, by applying certain mathematical formulation, instead of this volume integral, you will have a surface integral of this quantity d times dA. So you know it. So therefore, the internal quantity, integration of internal quantity is directly related to the surface of that system. Maybe you have seen, usually many textbooks draw a potato-like domain and integration of something here that is related with outgoing flux throughout its surface area. That is the meaning of this simple integration. Simply speaking, integration of outgoing flux of your displacement all over the surface, that is equal to the entire amount of charge inside your system. That is the simple rule we have seen our electrostatic part. So I'm just repeating same thing with you with one-dimensional specific case. So are you with me? So you have already seen it before in your previous courses. But point is, yes, I assume that you know this one. The main trick of our course is, instead of integrating our equation, so we just multiply this factor into our original Poisson equation. So our strategy is quite simple. Previously, we had a Poisson equation and it was integrated. That was our previous approach. And now, instead of this one, now we wanted to introduce this factor. d phi over dx factor is first multiplied to our Poisson equation, and that is integrated. So what is the meaning of this trick? Why we do this job? integrating the Poisson equation all over our deep substrate have no specific concentration or attention on certain part. So every part is regarded as the same. For example, in this integration, when you have a certain Poisson equation, even in this deep substrate, there is no interesting physical phenomena occurs, but they are contributing. Their 1 nanometer equally contributed to 1 nanometer nearby this interface, silicon dioxide interface. So they are equally weighted. But if we introduce this factor, weighting factor, d phi over dx, actually corresponding to electric field, then what will happen? Now, when you take this integration, only the position where you have a strong electric field is well concentrated. Only certain quantities at this point is contributing to your final result, because here, although it has a certain length scale, but since it has d phi over dx, which is quite close to 0, that does not contribute. So it is just goes away. Now let's think about a certain company's wage scale. So sometimes in a newspaper, we see that if you enter or join that company, then average wage level is something. However, everybody knows that this is not obtained by just you know. So let's say that. So this is your wage level, and this is a histogram, number of employee. And now let's say that this one. Then if that is the wage level, so for example here, most of them are just taking certain amount of wage. But you know, now let me just magnify. So now instead of that, this kind of a long tail, let's say that 100 times more wages than usual employer. If one person takes this amount of wage, then what will happen? This average value can be highly distorted by these exceptional ones. Quite similarly, when you just integrate your Poisson equation without any weighting factor, every position contributes to the same one. But when you multiply this weighting factor, electric field, then you want to just concentrate the position where very interesting thing happens, and electric field is high. So that's the reason why. That's the reason why we try to introduce this kind of operation. Okay. So are you with me? Of course, I'm not saying that this is it's quite general. For example, why that is just linear with respect to the electric field? Why don't we multiply square root of electric field, or square of electric field, cube of electric field? Why that is not tried? So of course people already tried it, but you know, this is the known way to make quite a good result. So we do just introduce this weighting factor. So now let's just have a look at our new Poisson equation. This is no longer Poisson equation itself, but multiplied with this simple factor d phi over dx. Then now we will have a second derivative and d phi over dx, and try to integrate it over this one. But that can be now here written as this form. Okay, So because this second order derivative is considered as once again derived with respect to x, and here we have d phi over dx dx. So they are cancelled. Then we will have d phi over dx and d phi over dx. So if this is too nasty to you, then instead of this second order derivative, please think about this guy as your ex and this guy as your ex. Then simply you will find that this is quite easy to understand. Now you have ex and dex, and that is obviously becoming so half of square and its d values. So that is quite easy to follow this manipulation. So so this one, the left hand side of your new Poisson equation or multiplied Poisson equation now becomes just electric field. Actually it's a second derivative. Square of electric field is occurring in your left hand side. And how about the right hand side of your new term? Then in this case you will have the original complication comes from Poisson equation, and the multiplication is done by d phi over dx and dx. They are cancelled, and that can be regarded as just d phi. So let me just clearly state, in this new form, left hand side can be expressed as only function of electric field, and right hand side term can be expressed as only terms of your potential. So therefore you can perform this integration. So once again, I strongly recommend it to you to do it by yourself. I can show many long derivation, but that is not your result. This is my result. You should do it by yourself. And if we take the integration of the above equation, starting from what to what, so now we think that, so I have to be a little bit careful. So when you have a look at this equation 4.14, what is actual integration domain? The integration domain is, in this case, is set from x to infinity. So in terms of our real space. And if you go to the electric field, then what will be the electric field? In this case, electric field would be just 0. And position x, what will be the electric field? In this case, we will have certain electric field at that point. And also, let's go to the electrostatic potential. What is the value of your electrostatic potential at deep substrate? Of course, that is just denoted as 0, but that is a reference point. And in this case, we have phi over x. That's the reason why when you have a look at this left-hand side, you can find that the integration range is set to be 0 to minus ex. Where can you find it? So this is the one corresponding to this left-hand side. And right-hand side, when you have a look at it, now this is interpreted as a d phi integration. So now you have a 0 to up to phi over x. So simply speaking, this one is corresponding to the position x equal to infinity. And this guy should be regarded as a position equal to a certain position x value. Okay, now same happens. This one is x equal to infinity, and this one is certain position x. So we do this integration. So let me just write down or display what is happening now. So what we are doing currently in this case is we must solve the Poisson equation everywhere inside this simulation domain, calculation domain. But instead of that, we just multiply d phi over dx, electric field, and integrate it over some domain. And integration domain is just selected in this way. So let me just introduce this will be the integration domain. One end is obviously x equal to infinity, and the other end is a certain position, non-negative position. And eventually what we will do is eventually we will move this x position to x equal to 0. If we really arrive at x equal to 0, then what will happen? Then we will have the potential at surface and electric field at surface. Potential at surface is really the quantity we wanted to know, surface potential, and electric field at x equal 0. What is it? This is actually the electric field at surface, and by considering the Poisson equation, the integrated original Poisson equation, that can be regarded as our surface, so silicon charge, semiconductor charge. So simply speaking, if we expand this integration toward surface area x equal to 0, then we expect that we will get certain relation between surface potential and surface electric field, or in other way, net charge density inside the semiconductor. That is general structure of our derivation. Okay, so now you will have this seemingly quite long, but once again, I strongly recommend you to derive this equation by yourself, not just following and trying to understand something. So your handwriting is really important in this stage. And now you will find that this is corresponding to your squared electric field at a certain point. Of course, by performing this one, actually you should have the squared electric field at x and squared electric field at infinity. But once again, we are using that information. If we go to deep substrate, there will be no electric field at all. So this guy just goes away. That's the reason why our left-hand side terms becomes just squared electric field. Wow, that is great, because when you just integrate our Poisson equation without any weighting factor, what was it? You got just electric field. You had electric field by integrating your Poisson equation. But now, with a new weighting factor, now you get not surface electric field itself or electric field at a given position itself. Now you have its squared value. Okay, so now you have this square, and by taking simple rule, is it really simple? Yes, that is really simple, because here we have only exponential and here we have only exponential, and integration of exponential function is really easy to do. So you will have lengthy, seemingly quite lengthy, but this is really straightforward. Please follow it by yourself. Then maybe you can be overwhelmed by many terms. Oh, how many terms? Actually, we have 1, 2, 3, 4, 5, 6. So there are many terms, but they are not that much difficult to follow, because you will have this exponential term and it will generate exponential, and integration of exponential will give you once again same stamp exponential something, and it should be evaluated at x equal to x and x equal to infinity. If you apply it to x equal to x, then you will have this term. And when you apply it to somewhere means that somewhere related with something x equal to infinity, then what will happen? If you go to x equal to infinity, phi becomes 0, and this exponential function will give you just number 1, unity. And where can you find the unity? So this is your unity. And how about this one? This number, just a simple number 1, gives you just potential, because this is phi integration, and this phi term now entered into this one. So now you clearly understand these two are originating from hole density, and this one is related with doping density. And quite similarly, you can find that these two are related with electron density, and this guy comes from another doping density related with another term, constant term shown here. So although it has 6 different terms, but that is not that difficult to follow, and you have to understand their roles. Okay, here we have seemingly many terms, but what is important is relatively these constant terms are not that much important, because we wanted to know the change of something, change of electric field by changing our surface potential or eventually gate potential. So this is not that much important, and because they are just fixed numbers. But here we have varying numbers for terms. Then now let's try to consider their relative importance. Everybody knows that this is linear terms, and these are exponential terms. Simply speaking, if argument is or magnitude of our input argument phi is close to 0, then these exponential terms does not play much important role. But if we go to very high and very okay, so if we have a certain normalization factor, something usually kBt over q, then in this case you will find that this exponential term will play the critical role, dominant role. Okay, so simply speaking, if I have x and y, and if I draw y equal to x, yes, this is the y equal to x, and if I draw y equal to exponential x, and if we have a certain point here, we have a dominance of our exponential term, and in this part actually it is just flat over our surface. So this is not showing drastic change, and in this case this linear function shows even faster movement with respect to our input argument. So simply speaking, here we have 6 different terms. So neglect these constant terms. They are not that much important for a while. So just neglect it. and this is corresponding to hole, and this is really important from NA, and this guy is not that important. And now we have one term comes from electron densities. Then now let's try to evaluate relative importance of these three terms. One term has the form of kBT over Q. Another term is having the form of phi kBT over Q. And the third term, that is important. Third term has exponential positive phi over kBT. But here we have a very important missing factor that is shown here. This is Ni square divided by Na square. What is Ni? In our usual room temperature case, that is 10 to the 10. What is your Na? In our example, it is 10 to the 18. So by calculating this ratio, Ni square divided by Na square, you will have the leading coefficient, unitless leading coefficient corresponding to 10 to the minus 16. That is the starting point of our evaluation. Now we have three candidates for dominance in this right-hand side term, and one guy shows the leading coefficient 1 and exponential. And another one is leading coefficient 1 and just linear. And everybody knows that since this is exponential, maybe that will play quite a critical role, but it has a penalty, strong penalty, given by Ni square divided by Na square. So it starts from quite a small leading coefficient. So now let's try to increase phi from 0 to quite a large number. So what I'm saying is starting from 0 and go to 1 volt, 2 volt, for example. Then what will happen to these three guys? So when we have the values quite close to number 0, then which one will be the dominant one? Of course, this one will be dominant one. Because you know this guy is exponential, but and after that, if we consider positive one, so that will actually minus phi, so that will decrease quite rapidly. And this one is linearly increasing, and this one exponentially increasing. But we have to wait for a while to eventually this fast growing term eventually catch up this slowly varying quantity and eventually overwhelming this term. So we need to certain amount of phi value to have electron dominant regime. Okay, we need a certain amount of bending to have electron dominant position at a given position. So that is the main result of our today's lecture. In order to, so when we just integrate our Poisson equation with weighting factors, then we will have the exact relation for surface electric field. But it states that eventually for high phi value, electron will dominate. However, it has a strong penalty. Penalty is not just 1,000 or million, but it is corresponding to orders of 10 to the minus 16, 10 to the minus 14. that strong amount of penalty should be overwhelmed or compensated by this exponential factor. So we need real high band bending, severe band bending is required to have this inversion phenomenon. So now, as I advertised once again, the previous relation equation 4.15 was valid at everywhere, and let's just have a specific value at x equal to 0. What we can do is just enter x equal to 0 position. Then now we have the surface potential. Simply speaking, surface electric field can be written in terms of surface potential. This is surface electric field, surface potential, and you know that surface electric field can be directly converted into your surface charge. So now we are now arriving at the final expression for QS. The total charge inside the semiconductor region can be expressed as simply just surface potential. So that is our main result in today's lecture. This is well known, and actually we have to practice again and again. And the comment I wanted to do today is this is not easily generalized. Generalization to more complicated structure that is not known. Actually, the only other exception where we have an analytic result is found by the only exception, additional exception, was found by Professor Tower about 24 years ago. So when he stepped down from IBM and joined into a university, he published a paper, and in that case, for a certain specific case, we can have a semi-analytical expression for different system. That was the only exception. Then this planar MOSFET cases. So generally speaking, the formulation we have is really to us really a gift from something. So since we know this analytic expression, we can just introduce some small modification to get approximate expression for QS and phi S. But in general, analytic form is not known to general cases. That is the thing what I wanted to say. And actually that is one of my main research topic. We are still trying to find out good approximation for phi S and ES. Okay, so now you have homework 5, postponed one. It was actually assigned to homework number 4, but now you have homework number 5. What you have to do is by next Monday, just to draw the relation between QS and phi S. That is one thing. And what you have to do is just to draw this equation 4.16 using some numbers. So in some sense that is really trivial, but please be careful. You never did the real calculation with Ni value, Na value, epsilon, kBt, blah blah blah. It is very easy to make many mistakes when you really makes your coding and calculation. You may use computer programs to make a beautiful graphs, or use your Excel, whatever. Every way is allowed it. So just to do it. And the real purpose of this homework number 5 is the second part. once you know this relationship between QS and phi S, it means that once you select your phi S, you immediately know your QS value. Then using this QS value and also using this expression, so please try to calculate VG, gate voltage. So let me just tell you once again. First select a certain phi S value. Then now you can calculate your QS value, charge. And when you know this charge and or electric field, then now you can calculate the gate voltage which actually yield this amount of or produce this amount of charge and this surface potential. Actually, the real process is the opposite. For example, you as a user of a MOSFET, you can select gate voltage. When you select gate voltage, by action of this Poisson equation, your MOS system will generate a certain surface potential and will have certain surface charge or semiconductor charge. That is the one. So this is an independent variable, and this one will be the reaction of your MOS system. But that is difficult to draw, or in order to calculate phi S starting from VG, that is difficult. So my homework number 5 just suggest you don't try to that complicated one. Instead of that, start from your phi S. Then you will find what is the required gate voltage to get certain amount of surface potential and charge. Do you have any question in this homework number 5? So I'm still worrying because studying about the difficulty of this problem. So in the remaining lecture time, within 10 minutes, I will show you the answer of homework number 5. Oh, that's quite boring, but please, since this is the early stage of our lecture development, so I will show you the answer. Then please try to reproduce. And if you are doing good enough, then please do your own exercise. What I want to ask you is, when you did it perfectly, then why don't you just change your oxide thickness? And why don't you just change your NA values? These are two parameters you can easily change and just to observe the behavior of your result with this one. But this is not mandatory. Actually, homework number 5 itself is not mandatory. So I will not check your everybody's homework submission. Just it is given for your own sake. Okay, so now let's have a look at the answer of homework number 5. I just draw equation 4.16 with the values shown Na equal to 10 to the 18 per cubic centimeter, and I assume a certain strange number for intrinsic carrier density. Once again, Ni value is about 1.1 times 10 to the 10, and depending on even literature, this value is not exact one. Because why it is not that quite much fixed? Because it is related with the effective NC value, so effective dose of conduction band and effective dose of balance band, and also band gap energy. So none of them is precisely known to us. So of course we have quite a good number, quite a reliable number, but depending on measurement, so they have little changes. So that's the reason why our Ni value is not exact, but I have used this value. So maybe you can use 1.0 or 1.1, sometimes 1.4, whatever you want, you can try. Then using this one, now you have this graph. This is your QS and this is your phi S. Well, how does it look like? This is what you have expected. So now here we have phi S equal to 0, and now here we have 0 charge. Please note that the meaning of our surface potential shown here is referenced to our deep substrate. So when we have 0 for this surface potential, it simply means that there is no band bending at all. So since there is no band bending at all, therefore it is obvious that we must have 0 charge collected in semiconductor. So this is quite much obvious. And when we go to positive surface potential, now we have negative charge. Okay, so don't be confused by different ones. Sometimes students just draw like this. No, it's not. This is we are having negative charges when we have band bending, downward band bending. And now we have a positive charge for negative surface potential. You know, this is originated from holes. So more holes are accumulated in this part. So that's the reason why we have a positive. Holes are positively charged. And eventually here we have a quite strong negative charge. Then they are coming from our inversion electrons. And here we have some moderate changes in our charge, semiconductor charge, and you know that is related with depletion behavior. So I think that you have already seen it before. And maybe some of you feel some strangeness in this drawing. I have seen these graphs in my previous textbook, but it looks somewhat different. So it is because in our usual textbook, everybody just draw it in this kind of a semi-logarithmic scale to show this behavior. So previous one was a linear scale. QS was taken as its linear scale, and now here this QS, actually the absolute value of QS is drawn, and I just introduce a logarithmic scale. So this kind of graph is usually called as a semi-logarithmic scale, and this one shows the orders of magnitude difference in our critical quantities. Of course, in this scale, this part is not very clear, but here this part is more exaggerated and we can have a clear view. As you can see here, if we have a flat band condition, then there is no charge at all. And when we increase our surface potential, then now we can have certain amount of increase. You know that in this semi-logarithmic graph, this shape typically related with the linear term. So when you draw log graph, then you will have just this is a logarithmic scale, and this is corresponding to linear dependency of your left-hand side, right-hand side term, and eventually you will have a straight line. This is straight line in this semi-logarithmic one that is corresponding to exponential phi. So now you can understand this is corresponding to the inversion, and this one is related to the depletion. But maybe you can find two dots. What are those dots? Those dots are introduced in this case phi s equal to phi b. So phi s equal to phi b, what does it mean is phi s is nothing but our tilde value at 0 reference to our tilde value at 0, and that is also nothing but phi value at 0 reference to our infinity value. And yes, so okay, so this means that when you have a look at just surface potential, you will find that at this point, at x equal to 0, your electron density at surface will be Ni. So let me just give you this answer. If you have a look at this point, then what will be your value of electron density? Your electron density will be just Ni square, sorry about that. Your Ni and electron value will be Ni square divided by Na. And now at this point, now it becomes, the surface point becomes really intrinsic. Hole density also shows Ni value. And if we go to this 2 times of phi b, yes, 2 times phi b, now you can say that electron density at surface point or interface point now becomes Na, and hole density instead becomes Ni square minus Na. So the historic reason of inversion comes from this way. Our pioneers just doped our semiconductor with Na doping density, and they expected that I can find hole density of Na. That was their original expectation. However, when they make a MOS system and apply certain amount of gate bias positively, then at this bias condition or certain surface potential case, they can find the same amount of not holes, electrons at the surface. Obviously, we introduce p-type substrate, but we can find quite a high density of electrons. So they thought that maybe that is related with electrical type conversion. Previously n-type, but it was converted into it was originally p-type, but it was converted into n-type electrically. So therefore they named it as inversion of their type. So therefore the onset of this strong inversion is defined as phi s equal to 2 times phi b. In our example, 2 phi b itself was about 0.47 volt. So 2 times means that about 0.94195. That is the required surface bending. Oh, then I have one question. Then if that amount of 0.94 volt is required, then can we just apply Vg equal to 0.94 volt? Then can we get a strong inversion? It is not, because this quantity is related to the surface potential. What we can control is gate voltage, and by changing gate voltage, we should change phi s, and when phi s arrive at 2 phi b, then eventually now we have a strong inversion. So that's the reason why this 2 phi b should be regarded as the internal quantity. Band bending should be 2 times the phi b, but in order to get that band bending, we have to do additional thing because there exists silicon dioxide. Okay, so therefore I have to stop here. But you know your lecture material already contains this homework, the entire solution of homework number 5. So please do your own exercise and homework submission, and we will continue this lecture next Monday. Okay, thank you.